Let's look at a pendulum. So a pendulum is a fixed point, an anchor point here, with a cord that leads out to a ball or a weight. And what happens is this ball is released and it swings down, gaining speed until it reaches its maximum speed at the bottom, then slows down on the way up until it stops over here. So the question is, what are all of the forces and the direction of the acceleration at the moment it's released? Or it could also be, what is it at the other side? So when it's at the top here, it's not moving. So the tension in the cord is zero. The only forces we have acting on the ball are the force of gravity. So this is our net force, so the acceleration is down. That is going to speed up the ball. As the ball gains speed, now there is a centripetal force. And what is that centripetal force? Well, there's tension in the line, so we have tension here, but we still have a force of gravity acting down, but now this is only a component that's working against the force of tension. So if we have an angle here, we know that this force of gravity in the y direction would be Fg cos theta. So our net force in the y plane would be MAC equals the force of tension minus Fg cos theta. But there's another acceleration that's occurring because there's a component of the force of gravity acting in this plane, and that's going to be F net equals MA equals Fg sine theta. So this is speeding up the ball, and this is acting as our centripetal force. So the problems we looked at before, the ball was traveling at a constant speed. In this case, the ball is speeding up, so we have two different net forces occurring at the same time with two different accelerations. In this question, we have a cone, and in the cone is a ball that's spinning around. So you can look at this sort of like this, like here's the cone, and you can see that if the ball was spinning around the cone too slowly, it would spiral down and end up in the bottom. But if it was spinning too quickly, it would start to rise out of the cone. So the question is, how fast must it go so that it's the perfect speed so that it rounds in here and doesn't slide down and doesn't slide up? So to do that, we need to look at the different forces involved. We have two forces because there's no friction here. We have the force normal that acts perpendicular to the plane. So if we have an angle theta in here, then we can make a right triangle, and this would be phi, which means that this right triangle gives us theta, and the angle across from it would also be theta. So when we break up Fn, we end up with an adjacent side, Fn cos theta, and an opposite side, which would be Fn sine theta. But we also have the force of gravity. So the force of gravity opposes Fn cos theta, and they cancel each other out so that the ball doesn't have an acceleration in the vertical plane. But the ball is centripetally accelerating, so there must be a centripetal force. That's going to be our Fn cos theta. So let's go ahead and solve this by starting out with the F net y. So in the y direction, we have MA is equal to Fn cos theta minus Fg. But it's not accelerating in the y plane, so this drops out to 0. Bringing the Fg to the other side, we have Mg equals Fn cos theta, or isolating for Fn, we have an expression for Fn, which is going to be Mg over cos theta. We'll be able to substitute this in our next equation, which is going to be F net x equals MAC, because this is the plane of acceleration, and that's going to be equal to Fn sine theta. This is the only force acting in the x plane. We know that AC is mv squared over r, And we know that Fn is mg over cos theta, so we can sub in for Fn as mg over cos theta. Multiplying that by sine theta, we have m on both sides, so these cancel. And we know that sine theta divided by cosine theta is tan theta. So on this side we have g tan theta, and on this side we have v squared over r. We can bring this r over with the gr, and we have tan theta. Taking the square root of both sides, we have gr tan theta. Now, I'm not going to do this derivation, but a ball that's hanging from a cord, like a tether ball, that spins around in a circle, that's going to be the same exact problem, except instead of a force normal, we have a force of tension. Here's a problem in which we have a car rounding a corner, and the road is flat. So we have a radius r, which is the circle of the curve here at this point. And the question is, how fast can the car go around the corner without slipping? Well, if we take the car and look at a side view, so here's the back end of the car, and we look at the back end of the car, we would see that we would have the force of gravity down and the force normal up. These are going to be equal to each other in opposite directions. And what is the force that drives the car around the corner? Well, it's the force of friction of the road pushing on the tires. So that's FF. So our plane of acceleration is in this direction, and we can solve for the max speed doing it this way. Let's first start out by doing an F nat y. So that's going to be ma equals Fn minus Fg. And our acceleration in the y-plane is 0. So we can bring this over to the other side, which is going to be mg, or we can just simply say Fn is equal to mg. Now in the x-plane, we have acceleration. So we have F nat x equals mac in this case, and that's just going to be the force of friction. So we know that AC is v squared over r, and force of friction is mu Fn, and it's not slipping or sliding, so it's static friction. We can replace Fn with mg, so we can say mv squared over r is equal to mu s mg. We have an m on both sides, and solving for v, we have v is equal to the square root of mu s g r. This problem is about as hard as it gets in terms of centripetal force problems. We have a car rounding a banked corner. Now we did this problem before, but we didn't include friction. So this time we have friction acting down the plane to keep the car from sliding up the plane, again, relative to the plane in that position. So we now have 3 forces instead of 2. We have our force normal acting up perpendicular to the surface. We have force of gravity straight down, and we have force of friction acting parallel to the plane. And as you can see, friction is now going to be broken up into 2 different components. The component of friction that's acting down is going to contribute with Fg to cancel out Fn. And the force of friction component that acts in the plane of acceleration is going to be helping to make the car accelerate towards the center of the circle. But remember, we also have a component of Fn acting in that direction. So we have a component of the force of friction and a component of Fn that are going to act as our centripetal force. We have Fg and a component of Ff acting down, which will be counteracting the force normal acting up. So what I did was I broke this down as cleanly as I could, but even with that, it's very hard to see. So let's start out and look at all of the different forces in the y-plane. In the y-plane, we have Fg down, then we have Ff acting parallel to the surface, but we need the component that's down. So we have theta here, so that FF is going to be FF sine theta. So in the down direction, we have FG and FF sine theta. In the up direction of the y-plane, we have a component of Fn that's going to be Fn cos theta. Then in the direction or plane of acceleration, we have the component of Fn acting towards the center of the circle. We have our opposite side, so that's going to be Fn sine theta, and we have the component of Ff acting towards the center of the circle, which will be Ff cosine theta. So let's go ahead and set up our F net y equation. So we have F net y equals ma equals, upwards we have Fn cos theta right here, minus, and what's acting down? Well, we have Fg, and we also have minus Ff sine theta. And it's not accelerating in the y-plane, so that drops out to 0. So what do we have? We have, I'm going to bring this minus Fg to the other side. So we have mg equals Fn cos theta minus, and I'm going to replace Ff with mu Fn sine theta. Now we can see we can isolate for Fn by factoring out an Fn and then dividing through by cosine theta. So that's going to become sine theta cosine theta. So that's going to be mg equals Fn, and that's going to be cos theta minus mu, and in this case it's going to be static, it's not slipping, sine theta. And again, solving for Fn, we isolate, and we have mg over cos theta minus mu s sine theta. Now in the x direction, we have two forces. We have ma, which is our centripetal force, and our two forces are Fn sine theta, the component of Fn acting to the center of the circle, plus the component of friction, which is going to be Ff cos theta. So we can replace this with mv squared over r equals Fn sine theta, replacing Ff with mu Fn cos theta, and we can factor out our Fn. So we have mv squared over r equals Fn times sine, the quantity, sine theta, plus mu s cos theta. So now we have Fn, and we can sub in for Fn here. So that gives us mv squared over r equals, and then subbing in we have mg over cos theta minus mu s sine theta, all times sine theta plus mu s cosine theta. And I'm going to do this next step all at once here. So we have an m on both sides, so those go away. And I'm going to bring the r over here, and I'm going to take the square root of both sides. So that's going to give us v is equal to the square root of gr quantity sine theta plus mu s cosine theta on the top, divided by cosine theta minus mu s sine theta. That's a difficult problem. In this problem, we're going to deal with work. And work is a separate unit that we haven't gotten to yet. That's coming up in a couple of videos later. But work is defined as a force parallel to a displacement. So these problems are often coupled with centripetal force problems, so I wanted to cover it here, which is if we have an object going in a circle and it's traveling at a constant velocity, we have a force that is our centripetal force that's acting towards the center. That's our net force. Now, in this case, it would be the force of tension if it's a string pulling us around in a horizontal circle. And we know that the velocity is perpendicular to this. So the displacement is perpendicular to the force. So none of it is parallel. So the work is 0 joules. Joules is the unit for work. Another way you can think about this is after it travels one entire loop, then we're going to say that the displacement is 0. So even though a force was applied, no work was done. Another problem that comes up frequently is a ball that's being spun in a circle with a spring. And with springs, the spring will stretch out, so the amount of force of the spring that's pushing on it, that force of spring, that's going to be our net force. And the formula for the force of the spring is kx, as we'll cover coming up. Springs. As always, if you enjoy this channel, like and subscribe. So I took this spring out of a clickable pen, and the first thing that you need to know about springs is that they can be stretched and that they can be compressed. And the important thing about this stretch and this compression is the change in spring length. So when a spring is just sitting there, it's considered to be in its equilibrium position, or any position at which we start at where it's at rest. So we could say it starts in this position, and then we stretch it an additional distance. But it's important that we're doing the change in length. So we have to pick an initial position. So for example, here's an unstretched spring. This drawing right here represents a wall or something fixed that the spring is attached to. So this is our initial position that we would call 0 meters. And as we stretch that spring out, it would go to a new position, which would be our x final. And it's that change in position that is x, the change in spring length from equilibrium. Now, you could also hang a spring from the ceiling. So this is our ceiling. And again, we would choose a fixed point while it's in equilibrium to be our initial position x. So what is the definition of equilibrium? This is when a spring is at its rest position, and then we choose a point at the end of the spring to be 0 meters. You could actually choose different points, but the best point to choose is the end of the spring. You could also choose the center of the mass or whatever you put on there. It would be the same result. So let's look at a couple of examples of what this looks like when you apply a force. We have a spring in equilibrium, so its x position is 0, and we hang a mass on it which applies a force and stretches the spring. That's our x final. So what's x, the change in spring length from equilibrium? That's that difference right there. Now, there's another type of problem in which we could hang a mass from the spring and say that this is our equilibrium. So this mass is just at rest hanging there. And if we apply an additional force, we could stretch that mass and pull the spring down further so that our new x, our change in spring length, is going to be the distance between these two initial and final positions. So what is x initial? That's our equilibrium position that we choose somewhere on the spring, or it could be the mass, which we label 0 meters. X final would be our new position, and then x is defined as the change in spring length from equilibrium. So when we look at the formula here on the reference table, it's given as Fs, for force of spring, is equal to k, the spring constant, times x. And if you notice, just like I've been saying, x is the change in spring length from the equilibrium position. So what is Fs? Fs is equal to kx. So that's the force of the spring K is the spring constant, and X is the change in length from equilibrium. So, what is K? K is how stiff the spring is. So if a spring has a very high spring constant, it's going to be very difficult to stretch. And if it has a low spring constant, it's going to be very easy to stretch. So what are the units of the spring constant? Well, we know that force is measured in newtons, and we know that length is measured in meters. So if we divide through meters to the other side, we're left with newtons per meter, the unit of the spring constant. So what does this look like when we graph it? So the force of the spring is equal to kx, and if we rearrange this formula so that k is isolated, we can have our change in y over change in x. So if we put fs on the y-axis and x on the x-axis, then when we graph this, we get a linear relationship. And what's the slope of the line? The slope is change in y over change in x, fs over x, and that's equal to k. So the slope of the line is k measured in newtons per meter. So let's go ahead and do a problem. Let's say we have a spring, and this is its equilibrium position, and we hang a 20 Newton weight on it, and the question is, find K. So that's going to be Fs is equal to Kx. The force applied to the spring in its new position is going to be 20 newtons. And we're going to divide that by what? Well, is it 0.2 or is it 0.3? It's neither. It's the change. And that change is going to be 0.1, the difference. So we divide through 20 by 0.1 and we get 200 newtons per meter.